Okay, so we're ready to start. Hi. Well, my name is Orkhan. Some of you may already know me. And I'm a software engineer, also training and consultant. And today we are going to talk about a concept of data microservices, which involve a few patterns and approaches that we're going to overview. So I will actually say that it's more of an architectural approach to what we are going to do. And кому нужно будет, кому удобнее будет на русском, всегда можно в конце ко мне подойти на русском, несмотря на то, что я буду говорить на английском и задать вопросы на русском. Okay, so we're ready to start, and let's start with the concept itself. So what's the concept? What it's all about? What is data microservices? I've heard this term, I believe, a few years ago somewhere in Spring Community. It was used and it had a wide, for me it was an extremely wide idea behind it. However, during last few years, I think that, well, it's not being used as wide as I would like it to be used. So just want to try to remember that concept for you, and the goal is that we start talking the language of patterns, start talking about the design and architecture of software by naming the concepts and approaches that we use, using correct terms. So what do you think about when you develop an application, when you're going to design it? Most of developers think about the application itself. So it seems like it's correct option, like I'm developing an application for blah, 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 and I'm thinking about what are the application models, what the application is going to do. However, think about your photo, which you're going to edit on your computer. What application do you use for that? A photo editor, okay? How many photo editors do you have on your computer? Zero. It depends. You may have from 0 up to n. So applications come and go. Today you're using one application, tomorrow another one, the next day you may use even 2 or more applications for editing a single photo. What's more important is that even having one single application, you may get updates for that. Some features are new, you get new features, and you have always some deprecated features that are gone. So what's important here? It's your photo. Your photo is your data. Only data stays. Applications do change from time to time. Features, you get new features and forget about new ones because they are gone. It's about data, not applications. So what about should we think when we design an application? One of approaches is to think about the data, because most of business applications that we develop nowadays are data-centric. I would like to say the sole role, but I will say the main role of applications that we develop is to do something with data. Input, output, process it. From that point of view, we say that a data microservice is a service that is very lightweight. Its purpose is to do something. Think about a method. Trivially, I will oversimplify it. Trivially, it's about a method that does something. It receives some arguments, it may receive, or even none, and it may return a value or not return. So a data microservice, think about it like a oversimplified, like a method that may have optionally input and output parameters. And such services are composable into pipelines so that you have feature services that do one single thing. Isn't it single responsibility principle? And I'm not talking about single responsibility in the means of I have a service with tens of methods that is responsible for one single area of our business or domain or anything. I'm talking about single responsibility over a feature, over a function. And you may use that kind of services to create your pipelines. Even you can orchestrate your pipelines by composing them in production, in a live system dynamically. So it depends. However, you'll have many of these services. And, well, it may become a developer's hell to remember how many services I have, what they do, what will be the pipelines. Then, why do we need such microservices? Is it just about the design? Of course, not only about design. There are some benefits and obviously some drawbacks in this model. So let's go and overview what are the benefits and which drawbacks we will have. The first thing I would like to notice is the contract. Such services are almost contract-free. Please note that I'm using the word almost because we're never contract-free, but almost contract-free because if you have a data microservice, you do not tell it what to do. It knows what it should do and it does one single thing. It just does it, and for a data microservice to do something, you have to provide it data and receive the output if it generates any. Again, we may compose such services in a pipeline and get a feature composed from such microservices. Then let's talk about communication and step back and remember such protocols like REST or any other messaging protocol that will be used for, it may be used for synchronous, asynchronous, it doesn't matter which protocol, but whenever you use your, whenever you organize your microservices using a direct connection between them, like direct communication channel, for example, REST or HTTP-based anything else, the feature is like service A communicates with service B directly. Everything is fine until everything works. As soon as you get issues like service B is unstable or service C simply gets unavailable, fails down, what happens? Client requests are not fulfilled, but that's not the main issue here. The main issue is that you may have data loss, because we're talking about data, not services, not the architecture. You may have one single service and it's okay for you, for your architecture, just because it does everything you need with your data. However, if you go to service-oriented or distributed applications, again, let's not think about services, let's think about data. We should do somehow develop our system in a way that it will allow us gain all the goals we would like to gain, but not lose any data. How we can do it? Well, one of available solutions is to use a shared storage between our services, like a database where we can store the data related to request and then kick another service like, hey, I've got request data for you, start crunching it. That's fine. Well, then we're talking about a storage or database or something like that. Persistent queue as a storage too. So from that point of view, we may simply publish request data or the payload to the queue. And other services who subscribe to that queue, they are kicked by the queue itself. Like, hey, you've got data, start doing something. So the benefits is that not having the direct connection between services, by decoupling them even more on protocol and communication level, allows us to do something in between, not to lose the data, to keep it somewhere. And if service fails, it can return back and again continue with its logic. So services are decoupled and composition and orchestration are made easier here. And again, I'll repeat it, if a service gets down, it may process requests later when it gets back. And the major drawback here is the additional cost of maintaining the message broker. Of course, we are talking about messaging streaming solutions, and there's a cost related to that. However, let's remember, we are in the land of, I will call it distributed systems, development of distributed architectures and applications. And I'm not using here word microservices because it's been used for many times during these 2 days. If it's distributed, and if you have many services and they are running in many instances, now we get closer to microservices, of course you have a person or a team who does the operations. I'm now talking about the DevOps, and it's their responsibility to make sure that queues are highly available. So as a developer, now we can say that as a developer, that's not a drawback for me, because for the project I work, they should have DevOps team who will maintain that thing. And if we have approved that solution, so as a developer, for now, I see only benefits, for now, for a while. So how do we develop such projects? And I promised to talk about Spring Cloud. So Spring Cloud has a special project called Spring Cloud Stream. And what it does, it simply allows you to develop applications with publish and subscribe semantics. So the basic idea and the architecture of Spring Cloud says that your application turns into your application core, so it contains all of your logic that you have developed. Now we add some input and output channels, optionally depending on your taste. And we have the middleware, which may be RabbitMQ, Kafka, or anything else. And we have the binder abstraction. So binder is provided by Spring Cloud. You may, of course, implement your own binder too. And that binder is the piece of code that ties your input and output channels to the middleware. So the Spring Cloud Stream is here to make things easier. And there's a magic number, 3. Remember that number. Everything is kind of about the magic number 3 in Spring Cloud. Maybe not everything, but hopefully in my presentation. So basic channel abstractions are provided by 3 simple interfaces. These are sync for input channel, source for output, if you generate data, and processor for both. These interfaces are very simple. Like, for example, this is sync interface. We have the name of channel, which is hard-coded input. Remember, hard-coded for now, please notice. Then we have input annotation, which takes the channel name as parameter, and subscribable channel class, which represents any subscribable channel. So we have input. Now, whenever a Spring Cloud Stream application initializes, if you do everything correctly, this will turn into a connection between the application and message broker for the channel named input. Same for source, but now annotation is called output, and the class type is more generic, it's message channel. By the way, if I remember correctly, subscribable channel simply extends message channel or implements. I don't remember that code exactly. Should have a look. And processor simply extends both. So these are interfaces. Now the development is simplified, again, the magic number, down to 3 simple annotations. It's about enable binding annotation, which is responsible for taking an argument, one of previous 3 interfaces, and it simply activates connection to the message broker. Stream listener annotation, which is for receiving the data from stream, and send to for streaming back to the output channel. A simple code example is like enable binding on the Spring configuration class. We assume that we're using Spring Boot with processor interface. Then stream listener for the input channel and send to. What happens here is that whenever a message is sent to the channel, you get it deserialized to the type which you have used. In my case, it's string for demo purposes. And whenever your method returns a value, that return value would be serialized and sent to the output channel. Now, what's strange here, the channel names are hard-coded. Remember? You may develop your own interfaces. And, okay, use any kind of input or output channels, any number, and then any names. However, if you can do so, why do we need standard interfaces? Why? There's an answer to that. Answer is that you can configure the name of channel in your configuration properties for your application. And this is why we have sync source and processor. And from the idea of the data microservices concept, you do not need any complex interfaces with many of input and output channels. You have to use simply sync source or output, sync source or processor. And using the ID of the channel, input or output, you provide the destination name, which will be used as the name of the destination channel at the message broker. Now, that's it. Everything is running. However, when you have to scale your project, your application, like there are many messages in the queue, and it's simply not enough processing power. You need more instances, because we're talking about microservices, and whenever you want to scale your solution and deploy more than one instance of your Spring Cloud Stream application, for load balancing one single queue, messages from one single queue between your microservices, you use a concept called consumer groups. It's simply about load balancing a single queue between many instances of your consumer. And it has one more option enabled, durability. Remember we said that whenever a consumer fails, if it comes back, it may process the queue again. But anonymous subscriptions are non-durable by nature with Spring Cloud Stream. It is a very opinionated framework, and you have to know how it works. So if you simply put a consumer, it goes, it fails, and you put again another one, it won't read the previous messages. For it to read previous messages which came while it was offline, you should always have a consumer group configured, even if you have one single instance of that consumer. And as soon as you have enabled consumer groups, durability is enabled, and you may now even initialize more than one instance of your consumer on different hosts. And you do it very, very simply by adding consumer configuration for input channels. Like consumer, you point the instance count, how many consumers will we have? The instance index for each consumer, what's the instance index? And there is a reason for that, why we need this count and indexes. This will be used for partitioning, which is next. And then simply the group name. That's it. You've got load balancing. But we're speaking about queues and message broker for communication. We may want not only to scale the consumer end, and we may like to scale the queue itself at message broker or even the producer. And this is where we start talking about the partitioning. It's when you need more performance and even consistency. And it's critical to have partitioning option enabled. And with Spring Cloud Stream, partitioning can be used. It doesn't matter if the queue message broker is partitioned itself naturally, like, for example, Kafka, or unnaturally, like RabbitMQ. So one single queue can now be partitioned to physical different queues, which work like, again, one single queue. And it requires configuration at both ends, for producer and for consumer too. And that's all configuration you need for the simplest case. For consumer, at input, we say that it's partitioned now. Depending on the instance count and instance indexes, it will be able to calculate which consumer should listen which partition. And at output, we simply say producer partition count 2. And it will be working in the partitioning mode. Now, of course, there should be more than that. Like, you may want to tune partitioning key expression. For example, I don't remember if that was calculated by the payload checksum, or I think payload ID is used for partitioning, if I'm not wrong. Correct me if somebody knows. I think it was payload ID. But you may want to input another different expression which will be used for calculating which message should be sent to which partition. And all of these settings are available in configuration. There's a quick and really not that big documentation available for Spring Cloud Stream. I will simply name which properties you may have optionally for configuring your application. It will be common properties for Spring Cloud Stream applications, like channels themselves are common. Then you may have binding properties for consumer, like consumer groups, for example. For producer, like partitioning and other things, like partitioning key expression or many other things. And there will be, of course, obviously, binder-specific properties, which contain options for exact binder, like for RabbitMQ or Kafka configuration. That's it. And we're finished with Spring Cloud Stream. That's so simple. What I'll add additionally to that, Spring Cloud Stream is built on Spring integration, on top of Spring integration. So this is the way how Spring Cloud Stream works, and maybe there will be a few more annotations or things to mention, but that's it. That's so simple. But if you wish to, for example, by default it serializes and deserializes using JSON. If you wish to change the rules of the game, you may simply use any Spring integration annotations, approaches. They are all available here. So depends on you. Have you ever used Spring integration? Okay, you can use any option from there directly within Spring Cloud Stream. But now let's talk about the data consistency, because we said that it's about data. Now, okay, it's a messaging solution, or call it streaming, and you'll be, wow, it's streaming. But when we use consumer groups, when we use partitioning, there are many instances. So let's remember the difference between monolithic and microservice applications, or even not applications, but architectures. Well, what should we focus on? We have user interface on top of each architecture. Let's forget that. It's that simple. But the business logic and data access layers, as well as database. So the main differences are that business logic is partitioned to multiple microservices, and database is sharded to many databases. Even maybe not all of them are a database at all. No SQL solutions, or just simply storage. Well, anything. So what we have here, the business logic requires transactions. And we may benefit from database transactions in the monolithic architecture. Well, what is a transaction? Let's remember. So it's a unit of work performed in the system like one single action. Like you've got a business process which should be treated as one single action, but it requires many actions to be done. So how you do that? You simply do many updates, deletes, creates, and you can even roll back if anything goes wrong. And in monolithic applications, in the monolithic architecture, is simple, because you have one single process, remember? One single process who's doing everything. And same process is responsible for committing and rolling back changes. However, oh, by the way, I like that shit icon there, because many people nowadays talk about that monolithic architectures are bad, because it's a single process. And you know what we got with microservices? Many of that. So transactions become more complex, because there are many processes involved to that. And the transaction itself is distributed. Now, please focus on the word transaction. I'm saying transaction, not database transaction. Now we switch to business transactions. It's about business. As well as the architecture was about data, the application itself is about business. We do not develop applications just for fun. Wow, I'm a developer, look, I've developed an application. No. Do you do so? I think no. You're earning money with that. So we should develop an application which is responsible for business transaction. From that point of view, it's simply more complex to observe and solve issues in a distributed environment. What's more complex to roll back. So how do we handle failed transactions in a distributed environment? One of available options is to try again later. In simple words, it's simply about part of failed transaction is put in the queue, as we discussed previously, and another service can pick it up and process later. However, well, not however, and by the way, the benefit is that transaction will eventually be completed, but the drawback is that we rely on other instances of our services not failing with the same part of transaction. Well, can you predict or can you guarantee that your service, or it's another instance, won't fail? What if the issue is in the logic that we have programmed, developed? It will fail, of course. So how do we fail transactions? Another option is to abort the entire transaction. So simply, something happens in a wrong way, and you detect that transaction has failed. We issue an undo transaction to all microservices involved, and this is also maybe called or considered like a compensating transaction. Now, they simply undo any changes they have made. But what's the problem here? First of all, who issued the undo transaction? And the second issue, which is more important, what happens if the undo transaction itself will fail? Again, dead end. I would say no. One of the possible solutions is to use transaction manager with two-phase commit. Now, what's the two-phase commit? Let's remember. We have microservices, many processes. All of the processes involved simply report to a single node to transaction manager that we're fine to commit. And if everybody's fine, it simply tells to transaction manager, tells to all participating instances like, okay, commit, cool. What if a service won't say I'm fine? Well, if it doesn't respond or says that, no, I'm not ready to commit, something is wrong, again, we say to all participants like rollback. Again, let's talk about the problems. So first of all, we heavily depend on transaction manager. If there's a single instance or single thing that you depend on, you are not decoupled here. And we're talking again about microservices. Not good. But okay, if we scale it, if everything works, it will be fine. However, again, it delays processing. Now, some people will argue with me, and I have a friend of mine who, whenever I talk about that, let's swap the transaction manager to something else, he says me in Russian, "Nahira." And you know what? Really, if you have 5 to 10 services, it's just fine. But what if you have 10 to 100 microservices, and with many of instances deployed thousands of services, tens of thousands all over the world, in many data centers, many cities for availability? It will start to delay. It is potential bottleneck. It's not a bottleneck. It is a potential place for bottleneck. And of course, it's complex to implement. However, you may simply use a ready solution from any other company which develops transaction managers, which are shipped with application servers. So it's fine. We do not need to develop that thing. But it starts to get complex when you need to integrate it with other systems. Other systems means subsystems. Your application may be just big enough that you cannot use a transaction manager, or it will be bad, not because of previous reasons, but also because you have to waste many time to integrate all things together. So I'm not telling that transaction manager is bad or do not use two-phase commit. These are cool things that saved many souls and many businesses in previous days. But today, when dealing with transactions, think about different approaches, because different processes, different business processes require different approaches to what we are doing. And a transaction manager with two-phase commit is simply not always required. In most cases, we use it simply because we use it. But you may think like, be open-minded, guys. I don't want to use it. Then what can I do? So event-oriented, or also called like actor-oriented approaches are available as well. So think about a coffee shop. Like many of you got coffee in the upstairs yesterday, today. So think about yourself. and you want to buy a coffee. You're in the coffee shop. So what happens? With two-phase commit, with the transaction manager, the whole process looks like a single wrapping transaction. And someday, threads will finish. What happens? All employees that are serving for you, trying to get your coffee done, they will simply stop. They'll work and stop until your coffee is prepared. Following the best effort model and compensating in process may be more productive. By saying best effort model, I mean unguaranteed delivery. Sounds weird, but it works. First of all, they make sure that you have paid. Okay, we've got your money. You won't go, or if you'll go, less to do, and I have earned money. That's cool. Then your order is sent to a message queue as a message. It's streamed down to the queue, which is attached to the cup. It's oversimplified, but it may be so. And if something goes wrong, we simply enter into compensation process. If you have not received your coffee, or you received something else, you ordered cappuccino and got latte, get what you want or refund. That's it. Sometimes, of course, they will waste coffee, but the overall process is efficient enough to say that maybe this is the most efficient model for increased productivity. So our goal is to increase productivity by having less to no bottlenecks. So let's talk about the architectural patterns. To develop such systems, there's a major pattern which is called event sourcing. It is about the event-centric approach when instead of saving the state of the event, instead of saving the state of the entity, we store the sequence of state-changing events. Now, to get a state of an entity, we simply reconstruct it by replaying the events which we have stored. And saving an event is atomic. It is simple. It doesn't require any transaction. It's one action. Save an event. And we also have a concept which is called event store in this architecture. So the event store behaves much like a simple message broker. It provides an API for other services to subscribe to it, and it guarantees, or at least should guarantee, delivery of messages, of events to all interested parties. Now, we may say that event store, it's a major concept that should be called backbone of event-sourced architecture. And by this concept, using the event sourcing, you get, again, that magic number, 3, remember? You get 3 major benefits. Events are immutable, and they store the full history of state changes within the system. Thus, they provide a detailed audit trail of what happened in our system. That means that you can look through events, and not only current state of the entity, but through all the history. What happened? Who did change that? And so on. So, next is integration with other subsystems. It's simpler one. It's publishing and subscribing. So they simply subscribe, and we publish events to other subsystems. And again, we also have the record of what was published to other systems. It's made easier, even for programming life. And the third thing is time travel. Like, you may determine the state of the system at any point in time. You can answer historical questions for testing, for, I don't know, business requirements, or simply go back and see what was wrong on next week so that our users failed with some things. Now, it's not that good, because there's a major drawback in this architecture. And the drawback is that, remember, state is stored as a series of events. And we have to replay all of them to construct or to reconstruct the entity state. Now, this may be a time-consuming procedure. You may have tens or hundreds of events, but you may also have millions or even more. But there's a solution to that, and it's very, very simple. We simply separate our logic, our model, to 2 separate models. One is called write model, which is the event store itself. Another one is called read model, the database where we keep current state of an entity. Now, there's another process, a different handler, which is responsible for updating the read model based on the changes, new messages from the write model. And it comes to a point where we can name another pattern, which is called CQRS, which stands for Command and Query Responsibility Segregation, and states that every method, well, I'll simply read it because it's very strict. Every method should either be a command that performs an action or a query that returns data to caller, but not both. So we separate the concerns. Now, that means that methods should return value if they do nothing, no changes, if they process no side effects. And if you have a return value, you cannot mutate state, simply. If you want to mutate state, do not return anything. That means from our Spring Cloud and Spring Boot, or even moreover, the architectural point of view, you simply separate to two services. Now you have the command side, which simply receives what you want to do, what you want to change, delete, and stores it as event. We do not need any transaction here. Then we have the query side, from where you get the entity state. Return me blah, blah, blah. And you have the event processor, which is subscribed to the queue and does changes to the data store. Well, what's more important here, the event processor and query side may be even used as a single, maybe developed as a single process, so that you may have no database at all. Like, keep an in-memory copy of what you need for even quicker access. And if something fails, you may keep a backup of your data, load it from backup, run a few event processing actions, so you have current state. Again, the magic number, three major benefits that such architecture gives is, first of all, consistency. Write model is consistent, and events are ordered, for example, by an auto-incremented ID, like, for example, or timestamp. Thus, transactions are simple. There are no transactions, it's one action. What's more important than really, most systems can be eventually consistent on the query side. Think about your business domain. Even the payment services can be eventually consistent. If you think about it and try to make some changes, you'll get to an idea that in most businesses, for most businesses, you may use such model. Second benefit is the data storage. For example, you may use a normalized data storage on the command side, like a SQL database, because it's an event, it has some columns that predefine structure for your event structure that tells you what data you'll get with this event. You know it, because you design your events. It's not about update, delete event. It's about my entity changed or something happened within my system, your business process. And you may use denormalized data at query side for quicker access to your data without any joins or an in-memory structure like that. And the third thing is, of course, scalability. As we have separate services for command and query sides, we may scale them separately and using different approaches. Like, you may have single service for command side and many for query, or vice versa, or any other approach. They are scalable separately. And simply to summarize everything that we discussed, there were many different things here. So I won't remember the contract-free option, but it's almost contract-free. But the main thing is that using direct access from service to service, using direct communication model, we may have issue like data loss. So we decouple everything by using message broker in between. And remember, somebody somehow should make sure that it is highly available. But this is DevOps responsibility. We may use Spring Cloud Stream as one of the options in Java world, in Spring world, to develop such applications. And it simplifies everything down to 3 simple interfaces, 3 simple annotations, and introducing consumer groups for scalability at consumer side, for scaling overall solution at producer or queue sites partitioning. But we may have data consistency issues because we have many processes involved. And again, we may have an option using one option is use transactions for that, distributed transactions. However, you may also benefit from event sourcing. What's more awesome, CQRS plus event sourcing patterns. And you've got an architecture that allows you to develop data microservices, which are lightweight pieces of code represented as a single service. They are data-oriented. They do something with data. In, out. You may compose pipelines of your business process using that microservices. They are even more reusable, more decoupled. They are more simpler. If you need to fix, you change a single microservice, push it back to your cloud or your server, doesn't matter what. And then again, design the pipeline, and you may orchestrate such pipelines even dynamically, if you wish so. And that's it. Thank you. So, my final words would be like, call me a good guy or a bad guy. I hope that you've got some idea from what is data microservice. And if you like the concept behind that, you may contact me. And you may vote for me as a speaker if you wish so. Any questions? So that means that you understood everything and the presentation was cool because it was simple, or you have understood nothing. Yeah, one question. We have one.
Hi. I think it's bad idea to use increment.
Sorry, can you please a little bit louder?
I think it's a bad idea to use increment in the database. Why we don't use ID?
But we do not use intermediate database. We use message queues. That was just an idea that we need a storage somewhere to keep something there and then to get from there. And we have simply passed to message queues because, yeah, really, an intermediate database is not good. But the queue being persistent, it may store data. Yeah.
Thanks. It was great. And can you say, please, about any drawbacks of such kind of architecture? What about the size of that event store? If our data is quite big and we are a new data, what about that?
So, about the drawbacks of the architecture and the size of event store, is it?
Yeah.
Okay, the major drawback is the eventual consistency. Because whenever you do an action, you want to update something, you have to wait. You cannot get the answer right now. Like, think about post, redirect, and get pattern. Whenever you make a post, and if you receive the data right now, you have a chance not getting the final version. Instead, you may make a post. Instead of the answer of the entity state, you get a redirect and be redirected to the get endpoint, which you can poll until you get changes. So eventual consistency is the major drawback, but it's not a drawback if you scale solution enough to get as small as possible eventual consistency, like as small as possible latency. For example, I've sent a comment, waited for 100 milliseconds or even less, and get the update. What about the size of event store? Well, the latency can be tuned, can be scaled. What about the event store size? It depends on you. For example, you can use Kafka as event recorder, and it may record unlimited. Depends on your limitations for the storage, how many hard disks you have. So again, you tune it based on your requirements. How many events will we keep in the store? It depends on your requirements. What is your business? Is it a bank? Is it Forex, for example, or anything? You may want to keep history for last 10 years, 20 years, or maybe just one last week. Again, what's your audit requirements, or what are the business requirements? You should define it. In most cases, in bigger applications, you will have many records of events. Depends on real situation. But of course, we want to keep everything. And depends on limitations of storage. Any other question? We have 5 minutes more.
Once more, please. And what about compensation mechanism? Are there any solutions out of the box? How can we process rollbacks if we've got 5 or 10 microservices involved in some operation?
You actually don't need a rollback here. What is the consistency about? You make sure that the data, the final states of entities are up to date and correct. If something is wrong, you simply kick it out and reconstruct it again from the event store. And you may keep snapshots of your data. For example, get a snapshot once an hour, keep 3 last snapshots, or once a day. And if you want to recalculate everything, you may get one of snapshots, which is correct, and simply reconstruct it using the events that arrived after that snapshot. And it will enable you not to reconstruct, not to replay all history of all events. So it's about scalability with snapshots, and yeah, of course, if something is wrong, you simply kick it out and reconstruct the state.
Thanks.
Okay, thank you. I'll be available if you want to ask more questions here.